This video is going to introduce our next unit, which is on chemical equilibrium, which centers around the idea that many chemical reactions are what we call reversible. So we've already been introduced to the idea of reversible reactions in the thermodynamics unit when we talked about delta G. So a reversible reaction, or this idea of reversibility, is a reaction that can proceed in either the forward direction, which is the way we typically think about reactions reacting, meaning that reactants are converted into products, or they can proceed in the reverse direction, which means that our products actually react to form reactants. And which of these things is going to occur depends upon the circumstances, depends upon the reaction conditions, whether a reaction will go in the forward or reverse direction. But we've heard about this idea before when we discussed delta G. We said that when delta G is negative is when our reaction is thermodynamically favored or spontaneous, and that means that our reaction goes in the forward direction. When delta G was greater than 0, we said that was thermodynamically disfavored or non-spontaneous, and that means that our reaction goes in reverse. And then when delta G was equal to 0, we said our reaction was at equilibrium, which means that it doesn't go in either direction. So we're going to be delving a lot deeper into this idea of equilibrium and what it means for something to be at equilibrium that we had mentioned when we were talking about Gibbs free energy in our thermodynamics unit. So what the state of equilibrium is the most stable state for our system. And we typically think of it as being the ideal product to reactant concentration ratio. The ideal ratio of product to reactant concentrations. In an equilibrium system, there's always going to be a little bit of everything present once that reaction gets going. There will always be some product and some reactant present. That these never fully go to completion. So all chemical reactions proceed in whichever direction brings them closer to equilibrium. Equilibrium is our most stable state, is the lowest potential energy for our system. So that is where all chemical reactions want to head towards. So our reactions always proceed spontaneously in whichever direction brings them closer to equilibrium. And where equilibrium lies, or what the concentrations are at equilibrium, varies wildly from reaction to reaction. So each system has sort of this ideal ratio of how much product to how much reactant is present in the system when it is most stable. But that ratio could be heavily skewed in either direction. Once your system reaches equilibrium, wherever that may be, whatever that may look like, your concentrations stop changing. That everything stays constant. When a reaction is reacting, if we're going in the forward direction, reactants are being consumed and products are being produced. But there's always some concentration decreasing, some concentration increasing. But once equilibrium is established, once equilibrium is reached, our concentrations become constant, they stop changing. So it seems like nothing is happening. However, at the molecular level, both the forward and reverse reactions are still occurring. For this reason, the state of equilibrium is often referred to as a dynamic equilibrium, because there is still stuff going on, that it's not just that all the reaction stops, because that is not the case. Reactants are still becoming products and products are still becoming reactants. But what's special about at equilibrium is that these two things are happening at the same rate. So at equilibrium, the forward and reverse reactions occur at the same speed. This is what is equal at equilibrium. People often get confused based on the name that, at equilibrium, there should be equal amounts of stuff, right? No, almost never do you have equal amounts of reactants and products at equilibrium. What you do always have that is equal at equilibrium is the rates of the forward and reverse reactions. So we can have drastically different amounts of products and reactants, drastically different ratios, and we describe that ratio using what's known as an equilibrium constant. Which is symbolized by a capital letter K. Please do make sure you use a capital K. Lowercase k is a different type of constant. Sometimes you will see this labeled as just K. Sometimes you will see it as KEQ for K equilibrium. Sometimes you will see it as KC for concentration, KP for pressure. They essentially all mean the same thing. So what the equilibrium constant does for us is it describes what's often referred to as the position of equilibrium. It's essentially describing the product to reactant ratio. for the state of equilibrium for that reaction. That when equilibrium is reached, do we have more products or do we have more reactants? And this is also related to or changes with the temperature. So when the value of K is greater than 1, again, this is essentially a ratio products over reactants. When K is greater than 1, that means we have more products than reactants present at equilibrium. And when K is less than 1, that means we have more reactants than products present at equilibrium. So K is essentially telling us which way does our ratio skew, which way does our reaction prefer to go? Does our reaction generally form more products or does it generally form more reactants? We refer to these as being product favored for K greater than 1 and reactant favored for K less than 1.